Guys, let's start. Yes, I am. Yes. Okay, I'm Vitaly. This is Chris. I work at LinkedIn. Chris works at eBay. For those of you who don't know, my company does a social network thingy. You can buy stuff on his company's site. But before we start, I just kind of want to know. The talk will be about kind of machine learning MapReduce stuff. How many of you have written MapReduce jobs? Keep your hand if you use like some platform like Hive, Pigs, something. Keep your hand if you use one of the cascading parts like Scalding, Cascalog. Okay, and just Scalding. How many people have experience? Okay, awesome. So we'll start. No slides, just kind of live coding. Cross your fingers, hopefully it will go well. So before we start, just kind of thing that will make my life easier, and actually it is things that we do use in our day-to-day, which is not part, actually it is now part of Scalding, but just not officially released yet. So one thing you can see here is this word local. So I'll see it. Scalding and cascading have local modes. So actually, in order to test our code, we don't have to ship it to our Hadoop cluster, which is great and especially valuable for talk. So we won't have to wait a lot of time to see the results. The second thing that you can see here is these case classes that I'm going to use. I just made up two case classes, and you can see that they extend Averagetxt. So both LinkedIn and eBay and other companies use Averagetxt for their data serialization. So Averagetxt, for those of you who don't know, it's a serialization format like Protobuf, Thrift, and others. And it's extremely nice to use instead of this long tuples because we can actually use case class. And there's a plugin that was developed in Berkeley that so Averagetxt has a schema, and the schema can be kind of a pain to describe. So all we need to do is just define our case class and say that it extends Averagetxt, and it will generate the schema for us, and it's really nice to use this way. The reason why we have this vars, it's like, don't stone us to death because of it. It's not our fault. It's because how Averagetxt works is it generates, first of all, like an empty object, and then it feels the data inside. It's kind of Java thing, and I guess the Berkeley guys didn't know how to handle it. So if you want to use it, then you'll have to set your variables as vars. So basically, the way to start a Scalding job, and let's kind of ignore all the imports, and let me kind of bring the screen a little bit up so everyone can see nicely. So I have my class. It gets args, and it extends job, which is a Scalding job. And that is basically all you need to do. And we'll start with something simple, and we'll show a couple of examples that go kind of more and more into depth. And what I'll use is Wikipedia in order to show our examples. And in Wikipedia, so that's what this first case class is for, is I just kind of removed everything unnecessary, and we just have the name of the article and the entire text of the article as one big string. And we'll use it in order to show some how easy it is to do things in Scalding. So let's start. So one of the things that we do, kind of the MapReduce paradigm, for everyone knows, there is the map stage and the reduce stage. Map is basically transformations, as simple as it is in the Scala collections. And actually, it's not where the most interesting stuff happens. It's, we take some data, apply transformation, we get another data. Most of the interesting stuff in our, at least machine learning careers, is how we do the reduction, because there's a lot more possibilities there, and our talk will be more about how can we do nice reductions. And I'll start with something very simple, like, for example, calculate the average length of a Wikipedia article. So let's just do that. So I'll just find function here, and I will load all the articles. And here is Chris Sievers here developed this awesome thing called packed hour source. So now it's actually part of the Scalding project. It was pushed like last week, and you can just read Avro in it, with it, sorry. So that's the way I read Hadoop data in Avro. So it's basically dir and plus articles.avro. So now what I have here is this packed Avro source. This article is actually a kind of a pipe that has articles in it. So every row will become this object article. And what we want to do first is to calculate the average length. So one way, the most naive way to calculate an average is to do two passes. We do one pass to count to sum all the lengths, the second to count how many articles, and then we divide. But in kind of real-life machine learning scenarios, we almost never want to do two passes over our data, because it's just inefficient when we are talking about petabytes of data. The second thing that we can do, we can kind of maybe have a tuple or some other intermediary object where we use it for both, for summing and counting, and then when we finish, we kind of divide one by the other, and we do as well. But since calculating average is something that is done quite a lot in Scalding, they have a function for it. So first of all types have this function aggregator, and it gets something called an aggregator, and we'll see what aggregator is in a second. And one of the aggregators is called an averager. So it's worth to mention what is algebra. Algebra is in kind of linear algebra, or not just linear, basically any type of algebra library that developed by Twitter, and they have a lot of very useful stuff there. It goes hand in hand a lot with Scalding, but it can be used also outside. It doesn't have to. If you have a lot of math operations that you need to do, and also it has kind of mini version of what you can find in Scala Z, like trace, monoid groups, semi-groups, etc. Then you can just use algebra, and it has a lot of the code for you. It doesn't have to be used with Scalding. So we use this aggregate, and one of the problems that I kind of immediately get, if we look at the averager, it's a monoid aggregator, and we'll get to it very soon, that has three type parameters. The first one is the input, then it's kind of the intermediary data, which is the monoid, meaning something that can be summed, and then they do a present, which is we take kind of our summing object, and we display it in some other form. So in terms of MapReduce, you can think about it as map, reduce, and map again under reduce result. So averager needs to get a double. So what we will do is, so pipes have just a function map, and it's very nicely the same kind of code you will do in just regular Scala collection API. So we can take our pipe of articles, and actually now we transform it over to a type of doubles. So now we have a type of doubles, and aggregate averager will work, and it actually will also return type pipe of a double. But that, since we aggregate over all of the articles, we'll get just a single number, and that number will be the average length of Wikipedia articles. And again, here I want to, well, yeah, there is no need to save it as Avro. We can save it also as TSV, CSV, and they have a lot of other formats. So, sorry, not string, it should be double. Double, and here is dir plus, and let's call it average.txt. Okay, and let's just call our function. And I'm kind of a Maven guy. I've been working with Maven for quite some time now. Still didn't really get used to SBT, so excuse me for that. And Maven has this really nice Scala plugin, which we can just do Maven Scholar run, and now it will run the entire code. And let's see kind of what we get. So now you see it's stuck on this compiler plugin, which is the Berkeley plugin that takes our Avro record classes and actually does the schema generation. For some reason, it's kind of slow, but hopefully we'll be on with our lives pretty soon. OK, so we have success, and if we look at, can we see here, cut Averagetxt, and you can see we have the number 27,525, which is kind of the length in characters of the average Wikipedia articles. OK, that's a nice start, but obviously we don't need scalding in order to do that. And a lot of the time that we don't want it to do just average. We want to understand how our data looks like for each variable, and we want to get additional features. For example, the average, the count, the sum, and also the standard deviation, the skewness, the kurtosis of our distribution. And actually here, Scalding has created something for us as well, and I will show you how we can also generate an aggregator that is not necessarily predefined in Scalding. So we will create now a new aggregator for us, but it will use something. So let's look at this class. Algebra has a class called moments. So moments is a pretty nice, if you see the case class here, has like parameters, and again, it has also a group for it. So the groups can take all these parameters, and for those of you who don't know what group is, it's basically like a monoid, but with negation and subtraction. And it calculates the count, the mean, the variance. Well, the standard deviation is just the square root of the variance, the skewness, and the kurtosis. So let's try to, but here you can see it's a case class. It's not an actual aggregator. So let's see how we can create an aggregator. So the way to do it is just to extend. So we have let's see, we have an aggregator class. Yeah, no, I want a different aggregator. Oh, never mind. Where is it? And we also have a monoid aggregator, which is, let's look at the aggregator first. So aggregator, like I said, it has this MapReduce map stage, which is the prepare, then the reduce. The prepare takes the input and just transforms it to some other type. The reduce takes two variables of these types and, well, reduces them, and present just again does another transformation on what the reduction was. And since the reduce and monoid kind of go hand in hand, then there is also the trait monoid aggregator that can, instead of the reduce function, can take a monoid and just use the monoid's own plus function, which is, if we already have a monoid for our data, is actually pretty useful. We don't need to lose data again. So extends monoid aggregator, and now that we will, again, we'll start with double because that is the data we have. And let's take what we will reduce on will be moments. And what we will eventually kind of output is list of any, and I will explain in a second why it's any. So like you can see, we have three functions to define. So the monoid is just the moments group. Obviously, every group is a monoid as well, so we can use groups here. And we have the prepare, so we need to take this double that we get and somehow to create a moment out of it. And actually, moments has an apply function, which, as we can see, takes takes a single value and returns a moment object. You can look at it as the zero of the monoid. And we need to also present the data in the format that we want. Let's see if it's okay. And well, here I'm going to do something a little bit nasty, but to list. That's why it's the list any, because it's just a tuple of 5 elements, and I don't want to write out each element, so I just made it a list. And now the code to produce this data is actually, again, very, very similar. Now that we have this moments aggregator defined, again, we read the articles, we transform it into doubles, because we actually don't have to transform it into doubles. One other thing we could do here is just start the aggregator with an article and have it just return moments, and the same application, just we can do it here, right? So text dot length dot to double. So we can also that's what the prepare stage is for, to kind of get your data in the format it's supposed to be for the reduction stage. And here, instead of the averager, now we have the moments aggregator, and hopefully I haven't made a mistake. And just list of any, and let's call the file moments. Yes, and let's just run this function now. Wow, that's interesting. It's stuck. Okay. That's not supposed to happen. Oh, awesome. And again, clear, we'll do the Maven Scholar run. And hopefully this time we will get, so remember, one of the moments is the mean. So hopefully in the mean we will get the same number we got before, and we'll get other numbers as well. That is very useful for us to understand how our distribution looks like. Awesome. And now cut moments. OK, so now we have the elements, and we can see actually, yeah, the mean is still the same. We have, it's not the entire Wikipedia in order to, it's just 1,000 articles from Wikipedia. The variance is 9 and something, and this is the skewness and kurtosis. And actually now it kind of becomes much more understandable how our data looks like. Something that was kind of hard to understand with just one number, which is the mean of the articles. And this aggregate pattern is very, very powerful. So you can do pretty much everything with a monoid. You need to think about, OK, how do I sum? And just examples that are already exist in Scalding. So we have a priority queue aggregator. So if we want top n elements, it's basically a priority queue that sums itself, like we do a monoid from this priority queue, and it sums 2 priority queues and gives us the top elements in a single pass without us needing to sort the elements first, which is much more efficient. Another monoid, hyperlog. For those of you who don't know, hyperlog is this extremely efficient way to estimate cardinality. With just like 12 bytes of information, we can get cardinality. I mean, how many unique IDs, for example, we have in a data set with just 1% error rate. So we, again, estimating how many unique elements we have is naively can be done only by, again, sorting through all of our data and kind of doing the unique. So hyperlog, and they have count min sketch, and I'm probably forgetting Bloom filters. Bloom filters are also monoids, and you can just pretty much do all this kind of nice data sets using monoids. And if you want to aggregate your data and apply this monoid on, then, and also, by the way, obviously we don't need to do it on our entire set. For example, I could have done, find me the kind of moments of all the moments beginning for, just what the first letter of the Wikipedia article is. And the only thing to do here is just to do this group by and dot text and like the first element, and then we group by the first letter, and now the group by will be will get an answer for every letter in the alphabet. So again, kind of nice. And here I will let Chris to continue. Oh, sorry.
Vitaly, is this mine sitting in here somewhere? Okay, let's see here. Hopefully one of these has the what? Oh. Hey, there we go. Look. Okay, let me clean some of this up real fast. Cool. And there we go. All right, is that, yeah, okay, cool, that's visible. Okay, so I was actually going to go through and we kind of gave a similar talk a little while, just a week or two ago, and I did some stuff with Mahout, sort of pulled some clustering stuff out. But in fact, actually just a day or two ago, I taught an internal class at PayPal, and we basically started from what is this Scala thing, and by the end of the day, we basically wrote a scalding job to calculate TF-IDF on a bunch of stuff that we had. So I thought we'd just try and do TF-IDF actually, because that's kind of a fun thing. So if you've, uh-oh, something just went wrong. Oh dear. Let's screw this thing in so I don't do it again. Come on. So if you've never heard of TF-IDF, it's a pretty common thing for a collection of documents and a given term in a document. We want to know sort of how important is that term inside that document or inside the collection. And it's not a hard thing, but it can be involved if you were to go and write this in a bunch of MapReduce jobs. But I want to sort of, come on. Uh-oh. It looks like it went to sleep on me. Can you log in real fast, Phil? Sorry. I'm not sure why it just slept. So it's a, yeah, it's a pretty simple thing, but it has a few steps. If you had to do this as MapReduce, it would be really nasty. In Scalding, it's going to be pretty easy. So basically, there's three things here that we're really going to need. So again, I'm working on kind of the same Wikipedia collection, and we're basically going to, I called my things wiki articles instead. And basically, just to prepare, I'm going to read some articles. And I'm just going to rip out the title and the body. And just because I'm going to keep using it, I'm going to go ahead and split up the body by white space as well. So we've done some kind of ghetto prep on it already. It's not perfect, but it'll work for what we want. So TF is basically given a term and a document. I want to know how many times did that term occur in that document. Okay, so term frequency. So let's see what we can do. So we can take our articles, and so given a term in an article, we have to think about what are we going to put out. And we probably want to put out multiple things per article, right? So we're going to put out something for every term in the article. So we'll probably use something like flatmap. Okay, so coming in, I like to name these things coming in. So coming in, we've basically got our title, and we've got our, let's say, token array. And let's make a function out of this guy. So what are we going to do? So now the sort of really fantastic thing about Scalding is that this sort of articles.flatmap, this is the Scalding piece, right? And now I'm just giving it a regular Scala function to use. So let's see what we could do here. Basically, what we want to do is we want to go through for everything in the token array. We would like to put out basically the number of times that thing occurred in the article. Okay, so we could do something like, let's see, let's make a counting bag. And let's do a group by. And just to be a little bit fun, let's group by the lowercase things. And then, so we've got this guy. Let's do map values. So when I group by, I'm basically going to get a list of all the tokens that match this key. Let's just do map values, and let's get the length of each one. Okay. So there's our counting bag. And then what I really need to put out now is some sort of iterable. I am using a flat map. So I'll do something like bag.map. So for every essentially count in the bag, or count in token, excuse me. Sorry, this is when we go live. We just want to spit this out along with the document title because we're going to use this later. So let's do something like token title count. Okay. All right. So that's it. So if we were to inspect TF, we'd see basically we've got a type pipe of string int. Okay. Not so big, not so bad. So there's our term frequency. For every term and document, we know how many times it occurred. Okay. So now let's actually get the total number of documents. Well, actually, this one's super easy. We can just take articles, right? Well, we want all of them, but let's just, to be kind to our reducers, let's actually ask for the keys. So remember, articles is this guy who's a type pipe of, sorry if that's hard to see, but it's basically a type pipe of string and then array of string. So I'm going to get the keys. I don't need to send all this crap down. I do group all. So this is a shortcut for basically group by unit. So I'm saying smash everything down to one reducer. And then size. So let me show you size really quick, and then values, because I really don't care about having the unit attached to my value. So size, just as a quick detour, is pretty darn cool. Oh shoot, we don't have sources down, do we? So size is basically using Algebird and defining, basically using a monoid under the hood to map everything to I think long and then just summing, but using Algebird again. So it's pretty slick. In fact, you can call sum after you group, and basically it will find if you have a monoid in scope on the type that you're summing on, it will just do the right thing and go through and sum using that monoids plus function. So this is great. Okay, and so you know what? I know for a fact that at the end I'm going to use this guy as a double. So I'm just going to do something like that. There we go, cool. So D should be a type pipe of doubles. It is, in fact, it's only one double, so we're actually okay there. Oops. You can see that I forgot to call out some of this stuff. So let me just, we'll do this as we go. Apologies. You can see behind the curtain. Okay. So this guy, TDcount. So this guy is basically, I want to know, so I know how many total documents I have, right? So I want to know for a given term, how many documents did it appear in, right? Because our IDF, our inverse document frequency, is basically a ratio of the total number of documents and the total number of documents this guy appeared in. So it's actually not so bad. It looks almost just like term frequency, except we're going to flip it. So let's go articles, and we're going to put out, again, we're going to use flat map. And we'll use something like case, when I have title array. And this guy is a partial function, so it really wants this partial function notation. OK, so what do I want to do? Basically, I want to walk through my tokens in the array, and I want to spit out that token and the title, and then I want to count up all the titles that I ended up with at the end, right? So there's one sort of sticky point, which is I probably want to do something like make that guy a set first, so I don't spit out too many things. And for some reason, it really doesn't like it if you don't specify the type here. And then this guy, I'm just going to map So this guy's like a token. Oops. And then I'm just going to spit out the token and the title. Okay. Am I missing some? Okay, we're good. So we've got that. Okay. Then we want to find out for a given token all the titles it appeared in. So I can just say group in this case. So group is kind of sugar. Did I miss something here? I missed a paren, didn't I? There we go. So in Scalding group is sugar. If you have basically a tuple of arity 2, it will just group by the left one in the tuple. And then I'm basically going to just say size again. Why not? So at the end of the day now, this pipe basically is giving me, I have a count token and then the number of articles it appeared in. Okay, so IDF, let's bring these guys together. So a really slick thing that is in Scalding is basically this. I can say TDcount. I have to group this guy again, unfortunately. It's just a syntactic thing. Maybe we'll fix that soon. Then, excuse me, I don't need to group this guy. I can just cross. There we go. And basically, I'm going to cross this guy with D. So I know for a fact that D is actually just this one thing. So what this will do is rather than spawning a reduce phase, it will basically just take this and ship it off to every mapper that TDcount lives on, and I'll have access to it there. So if we were to just sort of interrupt right now and look, we'd say basically this guy has a string long, and then it's got this double appended everywhere. Okay. So then all I have to do is basically map this guy, and I've got a case. So I've got sort of a nested business now. So I've got this guy, which was a token, title, and I don't know, just call it, excuse me, token count. And then this guy, which is like doc count maybe. And we'll send this guy to, what do we want? So we just want something like token, and then we actually want math.log, basically dot count divided by count. Okay. Why are we not? Yep, everybody's happy. Okay. So now we've got our IDF. We just need to get this guy back together. I'm probably running a little low on time. Are we okay, actually? I've got 15 minutes. Okay, so I'll leave this guy filled in just for fun. So basically the last thing is, all we have to do then is get the IDF thing grouped up by token. That's this IDF group. We're basically going to take TF and join it on the token again, right? And then we're going to call map values. So in Scalding, when you have essentially a join, or a group rather, essentially it holds the key fixed and you have access to the value set. There's a map values and a map values set. So the map values is smart and will happen on map side as much as it can, whereas the map value set, if you need the entire bucket to calculate something, it'll actually force down to reducers. So we use map values when we can. And basically all I'm doing here is basically say take the token, and for every token in title, basically spit out the TF IDF score for that guy, that token in that document. So the term frequency times IDF. I don't need whatever I grouped on. I'll throw it away. And then I write this guy out, and let's see if it runs. So I've got a little runner set up. We'll find out if it actually works. If not, we could always fall back to Maven. It's run before, so let's see. I'm running it in local mode essentially again. Uh-oh. Oh, you know what? That's the guy I meant to work in. And I just forgot. Well, let's try this again. All right, here we go. It takes a little longer than averaging, but hopefully not terribly longer. So it's running. Yeah, do you guys have any questions while this really giant computation is going on? Yeah.
Can I ask what version of Scala are you using? Is that 292 or 210?
This one's, I think, 293. But I've run the same thing in 2.10 and it works just fine.
210 and 420?
Yeah, yeah. That Avro plugin doesn't work nicely in 2.10 until somebody decides they want to go and fix it for us and make it work in 2.10. If anybody wants to do that, I'm sure both Vitaly and I'd be super happy. Is this guy still running? Yeah. Other questions? Is that a question in the back?
Yeah. So why did you say that this runs better on Scala than, say, MapReduce?
Sorry?
Why do you say, like, calculating TDF?
Oh, sure. Because you see basically what I've written here, right? So this actually spawns 3 MapReduce jobs. In fact, I can show you the graph if you want. It'll spit out a graph. Maybe we can do it afterwards because it's nice if we have time. But essentially, MapReduce is a functional thing by nature. And sort of writing it in this functional way is sort of agrees with me. But in terms of just like general use, there's a lot less boilerplate going on here, right? I sort of describe what I want to do and let scalding and cascading sort of plan it out for me and do it in the right way. The other thing is that in using this sort of typed API, we're really very, very close to regular Scala collections code. So almost all of my development, I do it like in the REPL or something on a local set and play with stuff and then just kind of change, how I read the data and how I write the data, and it's almost identical. So in terms of productivity, I find I'm much, much, much faster using this. Yes?
Does it run on Spark too?
Scalding does not run on Spark. I think the cascading guys are looking at running on Yarn, but Spark has a really similar syntax. So all the stuff I did here, you could write in Spark with very little changes. In fact, there's somebody trying to kind of unify all of them. Maybe it'll happen, maybe it won't, but it would sure be nice because there's another thing called Scooby and another thing called Scrunch. So it looks like maybe this actually ran. Yeah, here we go. Right, and so, okay, so we were a little ghetto in our splitting, so we have some weird characters, but then we get down to things like 0. But if we wanted to find something interesting like the, it's probably in here somewhere. Yeah. So the appears in a lot of places. You'll find usually the is not that important. I know for a fact that from the last time we gave this talk, like there's Anarchy was like one of the first articles, so we could find like whoops, let's do it from the start. So like Anarchy is really important to anarchism, and not as important for Mamluk, and not quite as important for porn actors apparently either. But anyway, you can see what it does. It's pretty nice. So anyway, I'll hand it back to Vitaly.
Okay, so let's see now what kind of what other things we can do very nicely with the Wikipedia data and what we saw here that Chris did with the TF-IDF. Okay, let's go back. So what I'm going to do now is something that is called, I will try to find similar articles on Wikipedia. And the way to find similar articles is, again, at least one of the ways, is to see how matching their words in their frequency. So if 2 articles have the same words in the same frequency, we can say, okay, these articles are kind of matching, and we can produce a score. And the similarity function I will use is called cosine similarity. Basically, it takes all the words in both articles and multiplies the frequency of the pairs of the same word in both articles and sums all this together, and we get a number. So there is a way, kind of short way to do it, and there is a long way to do it. And I will do the short way, and I'll leave you as an exercise to do kind of the longer way, because the short way is actually pretty nice. We will use the Scalding matrix API. So Scalding has a matrix API that does a bunch of cool stuff, and let's try to make it work. So let's see. We have the class here that article word count that we used, and let's article word counts, and well, we can use it here. Yeah, but let's just read the data that Chris has just wrote. Let me see if it's called word counts dot avro. So again, this data is saved in an avro format. Packed over source, everything is nice. So now there is a way to transform a pipe to a matrix, and let me show you how can you do it. So there's map to matrix, and basically what map to matrix gets, it needs to start from our class and to transform it to a row, column, and value. What is kind of very, very nice about the matrix API in Scalding, that it doesn't really tell us that rows and columns have to be integers. It doesn't have to be indices. We can actually use strings and whatever we want, because it's a sparse matrix representation. So it's just these tuples of row, column, and value. And since it's a sparse matrix, there is kind of a lot of neat ways to make it very nicely parallelizable between a lot of machines. So let's just do it. So we have this word count, and we need to get word count dot. So name is Oracle word, and I have it in doubles here, the count. So now we have a matrix of string, string, and double. And now that we have the matrix, we can do a lot of kind of nice matrix operations on it, like, for example, row normalize. And we can see here we have kind of free normalization. And the reason why I do the normalization here, because I don't want it to appear that two very long articles are similar to each other just because they're very long and have, just by sheer coincidence, a lot of similar words. I want to kind of normalize the effect of the length of the article, so I'm normalizing it, and here I'm using L2 normalization, which is the square root of the sum of squares of the frequencies. So basically, the sum of squares of all the frequencies will be equal 1 now, and now when we compare every article to itself, we will get 1 instead of some arbitrary number that is a kind of function of the length of the article. So now that we have, let's kind of call it val mate, and now it comes to, so like I said, cosine similarity is basically just a matrix multiplication. So all we need to do here, and instead of multiplying the entire matrix by the entire matrix, I will just pick one of the element, and like you see, it's actually asking me for a string. So let's say a Wikipedia article of Audi. Can try anarchism, I think one of Chris's favorites, and we can just multiply it by the matrix. But we actually need to transpose it in order to get, well, this whole row column stuff nicely. And again, think about it. It's just math. The multiplication is the dot product operation of matrices here, and writing this one line of code is, well, yeah, I just really tried at home. We will post the code on GitHub in order to see how much code this one line saves. Yeah, even in Scala, even in Scalding itself without the matrix operations. So, and just because kind of let's just pick the top 100 elements, because when we multiply a row by a matrix, we basically get another row vector that will only have the titles and the similarity scores. So we select the type elements, and then, like always, we write them. Let's write them to a type TSV of string and double and call it dir plus matrix.txt. Okay, that's the entire code we need to write to do a multiplication to get the most similar articles to the article Audi. If we want to get a matrix of all articles with each other, what we need to do is just to remove this get row, and that will give us the entire Wikipedia similarity between all articles. So I think that's really, really cool. And the fact that, again, obviously I will show it on my local machine now, but it's the same code that goes into the Hadoop cluster. You don't need to change anything besides perhaps this local thing. And actually, you can also simulate. Scalding also knows how to work with local HDFS mode. So if I write here HDFS, it will actually spin up a Hadoop on my local machine and will run it as if it was running on real Hadoop. So let's just run matrix here. Go to our beloved terminal. Hopefully it will work. And again, that will take a minute or two. So any questions? You don't. 2 minutes. Okay.
Do you have it available somewhere?
The source of what?
Your talk.
Hey, like I said, we will post it on GitHub and go to the SF Scala group and we'll post it there. Anything else?
Oh, one thing that's not immediately obvious. Well, probably
Yeah.
One thing that's not immediately obvious here also is that essentially it's doing compile time type checking all the way through that type. So if you've ever run things in regular, cascading or pig or hive or something, and 6 hours into the job you added a double and something that doesn't add the double nicely, the whole thing barks and you just lost that 6 hours. This essentially prevents that at compile time, which is a really fantastic thing. And it goes all the way through to basically write out.
Yeah, I had another extension on that because I know on object cascading, everything's essentially an object, and you always have to cast back and forth. So you guys are still doing the underlying casting.
So scalding, yeah, is essentially it's basically there's two APIs in scalding. There's three. There's the matrix one, but there's the typed one and the fields one. And the fields one happens just like regular cascading. You throw around tuples which just have stuff in them. The typed one essentially has been a little bit, they're being a little bit tricky and passing around tuples that have exactly one thing in it. And scalding is smart enough before it hands it to cascading to figure out that you have the types link up all the way through and that there are things that will actually play together.
So I'm curious because I know one of the differences with Scooby was that they don't have that underlying casting.
Yeah.
Do you know, I mean, because I know you guys were on Scalding, but does that actually buy anything, or is that just them saying like, well, we don't have this?
Well, no, the typed API in Scalding and Scooby are almost identical.
Yeah.
I mean, they're, for pretty much all functional purposes, they're really identical. And I mean, at eBay, like half the people in our group, in fact, there's another eBay guy who's going to give a talk next in this room. He's going to talk about Scooby. He uses Scooby, and half the group uses Scooby, and the other half uses Scalding.
There's like an internal war.
Yeah, it's a very low-grade war. And it all works out perfectly fine, actually. They really interop pretty nicely.
Okay, so here are the results. As we can see, we did something right by Audi getting, well, basically one as a similarity. We can see that the third one is auto racing, the fourth one is armored car, assembly line, and legally. So I don't know why African American is so high there, but we don't have too many articles, so it just. Does anyone know who August Hirsch is?
Founder of the company?
Let's see. We have this tool on Google and that links to Wikipedia. And August Hirsch is a German engineer pioneer and actually the founder of a manufacturing giant that would eventually become Audi. So as you can see, it's actually worked. It actually worked. So it's pretty exciting about that we didn't fail live. And it was a very simple and it's hard to stress like how simple this code was. So obviously there's some TF-IDF needs to be done in order not to get two articles that similar because they have the word B or the word A in them a lot of time. But once we did the TF-IDF, normalization is a single line, multiplication, single line, and that's it. We write it, so that's the end of it. Any other course have for me or Chris.
It's pretty easy, like in the TF-IDF, it's pretty easy to basically take that like document frequency or term document frequency pipe and siphon off the ones that appear in like 80% of the documents, populate a map or something, call those stop words, and then again cross that map back into the other one to remove them.
I have more of a question about if you guys run into, so I've run into this not in MapReduce, but one thing with this Scala collections API, which essentially this matches, is it's really, really, really easy to introduce complexity, exponential complexity.
Yeah.
Now for me that means something that should run in 10 milliseconds runs in a second, but for you that could potentially mean a job that's supposed to run in an hour takes 2 days.
Well,
I mean, how often do you guys run into that where you got to really go through and like?
So for me, that very infrequently.
Yeah.
Usually I think it's hard to some extent to introduce the complexity in like the actual scalding flow. Whereas if you're still using collections inside, of course, the sort of the functions you're passing in, right? You use collections code, and in that case, the thing's taking a second instead of milliseconds. It probably slows your job down, but my guess is that you can just pay so much I/O overhead and time for the Hadoop process that in general it's something I haven't run into much, I guess.
Well, I can say that maybe because the reason why Chris haven't run this much is because he's been doing it for quite some time now, but it's definitely something that happened. And one example is you can bloat your data very quickly. Like for example, if you do a bad join, then a bad join can really kill your job. A flat map, for example, if you take kind of list that you have, and now you instead of a list you have every element in a separate row, then your mappers can also go bad. So there is some fine tuning that needs to be done, and especially once you go to production and try it. It kind of, I think it's easier than Chris described to shoot yourself in food, but after you kind of do it a lot, it's the same patterns all over and over again, so you already know once your job kind of doesn't finish, you kind of know where to look at. That's it. Okay, well, thank you guys.